Okay, so in this video I'm going to talk about the extreme value theorem. This is the statement. If we have a function f of x that is continuous on the closed interval ab, it's important that it is a closed interval. Then this function attains its maximum and minimum values on the same interval. So let's consider the proof. So first, I made a separate video about the boundedness theorem, which says that if function f of x is continuous on the closed interval, then it is bounded on this interval. So here, this is a stronger statement, but we will use this boundedness theorem here. So by the boundedness theorem, so the function f is bounded on our interval. We will prove that the function attains its maximum value and the minimum would be similar. So these are two symmetrical statements. It's without loss of generality, it's enough to prove only one of them. So because it is bounded, because we are proving that it attains the maximum value, we are interested in boundedness from above. So because it is bounded from above, so there exists so from this it follows that there exists a supremum of the function f of the values of the function f of x, where x varies on the interval ab. So supremum of these values, let's denote it by some denoted by m. So now the fact that it is a supremum, it means that f of x is less or equal than m. So this is for all x, but also for every epsilon greater than 0, there exists such x that f of x is greater than m minus epsilon. Okay. So here, by the way, x belongs to AB, here and here. We consider only on the interval AB. So from this we conclude that we can we construct a sequence. So for epsilon, since it's for any epsilon, so we consider a sequence of epsilon that converge to 0. So let's consider epsilon n equal to 1 over n. or like it doesn't matter, we can consider any other sequence converging to 0. So for this epsilon n, so for any n, for any natural number n, we consider this epsilon, then by this statement there should exist such x. So for this epsilon n, there exists xn such that f of xn is greater than m minus 1 over n. So from this we conclude that so also f of xn, it's also less or equal than m, because this holds for any x because of this property, right? So so f of xn, so let's rewrite it this way. F of xn is greater than m minus 1 over n, but less than equal than m. So it is between these two values that are closer and closer together. So the left side tends to m when n tends to infinity, and the right side is always m. So basically, because of this, we conclude that so basically we conclude from this, we conclude that the sequence f of xn, so f of xn f of xn, it converges to m because it is bounded from above and from below by two sequences that both converge to m. So there is a theorem in that if a sequence is bounded if it's bounded from above and from below by two sequences that converge to the same limit, then this middle sequence also must converge to the same limit. So it converges to m. So now this sequence xn, it doesn't necessarily converge. So because xn by construction, like, it only satisfies this property, so it doesn't necessarily converge. But xn, it always belongs to the interval from a to b, right? So it is bounded. So xn is a bounded sequence. It might converge, it might not converge, but it is bounded. And we know by the theorem of Balzano-Weierstrass theorem that the bounded sequence always has a subsequence that converges. So by Balzano Weierstrass theorem, there exists a subsequence, so x and k, where k varies from 1 to infinity, that converges. Okay, so any bounded sequence contains a convergent subsequence. So because this subsequence converges, so let's denote the limit. So the limit of x and k when k goes to infinity, we denote by I don't know, like well, let's denote it x, just x. So so now we observe that the f of x and k, it also converges because it's a subsequence of a convergent sequence, because f, so let's write it this way. So f of xn converges, which we established previously. Well, converges to, yeah, we know that it converges to m. So the limit of this is m. Therefore, it follows that the limit of f of x and k of the subsequence of this convergent sequence also converges to the same limit. Also, the limit is also equal to m. Okay, so but by the continuity of the function f, we know that we can like we have a convergent sequence. So continuity basically means that we can replace the f and limit. So f of the limit of x and k when k goes to infinity, tends to infinity, is equal to the limit limit of f of x and k. So this is by continuity of f. And the limit here when k goes to infinity. So the now the left hand side here is equal to this limit is equal to x, right? So this is simply equal to f of x, and this limit is equal to m, because here it is. So basically we found a point x in the interval. By the way, it's also in the interval. So because the interval is closed, so the x is a limit of the sequence x and k, and because like, okay, let's write this. So x belongs to the interval AB because it is a closed interval. Because it is closed. Because in the closed interval, the limit of any sequence of points in this interval also belongs to this interval. So we found this x. So we found this x for which f of x is equal to m. So basically when we look at the beginning and at the end, so f of x is equal to m, And the m, if we recall what was m, it was the supremum of the function f of x, supremum by the interval from ab. So basically this concludes the proof, because we found the point x where it attains the supremum. So this therefore f of x is it is a maximum. It's not just a supremum, but it's also a maximum. Let's write it. It is also maximum value. By it I mean m. So like m is also the maximum value, and it is attained at the point x. So this concludes the proof.